along the bottom, find what you need, jump to it. If you want to watch the whole thing, awesome. But we'll be here for the next little while talking about experiments and observational studies. Of course, if you want to get all our AP Stats content as well as other exams, other courses, be sure to check out all of our social media pages, check out our replays, and be sure to subscribe to Fiveable itself. You can get all kinds of awesome content there. So this evening, I'll be discussing just a broad overview of the different purposes of statistical studies. We'll talk about explanatory and response variables that are present in all types of studies. We'll go into the distinction between experiments and observational studies, identify some key differences, and then also talk about these things called confounding variables that can potentially happen. Then we'll look specifically at experiments, identify some features of well-designed experiments. It's going to be a lot of vocabulary terms that you can quiz yourself on. And then we'll also close out by discussing the different types of experiments that the AP exam expects you to know. The three key types are completely randomized designs, randomized block designs, and matched pairs designs. So again, be sure to use the timestamps along the bottom to jump ahead to any of the things you want review on. We're going to do a big, broad overview first of the purpose of statistical studies. So there's a lot of different types of statistical studies you can do. There are surveys. That's a really common type where you try to gather data about a population via a sample, hopefully a representative sample. We did a whole other stream about surveys and the types of bias that can potentially be introduced in surveys. Be sure to check that out. But surveys are a special type of observational study, which also could be similar to an experiment in some cases. But those are about establishing association between multiple variables. So in surveys, typically you're going to ask a lot of questions or look maybe just at one specific variable about the individuals in your sample and try to use that data to make predictions about the whole population. If you're doing an observational study or an experiment, your goal is to connect one variable to another. So for example, can you identify which of several different exercise programs will help athletes grow their muscles the most? Maybe you're looking at if there's an association between attending Fiveable streams live and getting good grades on assessments that come about those units. Or maybe you're looking at, does the outdoor temperature impact the amount of drink sales? Maybe if you're selling waters or Gatorades as part of a school fundraiser, does how hot it is outside impact how many drinks you sell? To some of those questions, you'll probably answer, yes, there might be an association between those. Maybe there isn't an association between those variables. But either way, one of those variables is probably the explanatory variable. One of those variables is the response variable. And so in statistics, when we're doing a study, the explanatory variable, you might have called it an independent variable in a science class. It's the variable that we're going to use to help explain a change in another variable. And if we're doing an experiment, the explanatory variable is going to be the one that we have control over, that we decide what to do, what to give out to the individuals in our experiment. And in one of the examples I gave earlier, I think outdoor temperature could potentially be an explanatory variable. If you know it's super hot outside, that might help you explain how many drinks you sell at a certain event. It's not the only variable that explains how many drinks you sell, but if it's super hot outside versus super cold outside, that can potentially influence the amount of drink sales. And in that case, the drink sales would be the response variable. It's the variable that is the result of changes in the explanatory. It's the thing that we could have predicted by using the explanatory variable, or most commonly, it's measured as the outcome of a study. So if you're reading a situation and you can't tell if there's something that's like being predicted or something that's the result of something else, if you're looking at a description and you notice at the end of 6 weeks, they measure something, that thing is usually the response variable. And so as I mentioned earlier, we could potentially say that drink sales can be predicted by the outdoor temperature. And so the drink sales can be the response variable using the temperature as the explanatory variable. So let's go ahead and take a look at some checks for understanding here. And I'm going to pause for just a moment if you're watching on replay, because I do notice I did have someone just hop in live. If you are here, we've talked so far about explanatory versus response variables. If you could just give me a little bit of like, yes, I've heard of these before, or no, I haven't. I might need to reset for a second. If you're watching on replay, again, be sure to use the timestamps at the bottom to ensure that you can bounce ahead and check out what's going on. But so far, I have been going as if there's been no one here and it's just going to be a replay stream. So if you are here and want to get engaged, be sure to say hello in the chat box on the side. Otherwise, I'm going to keep going forward as if you're watching on a replay, and it'll be kind of me just doing a lecture style. But I do want to get it interactive. I want to make sure that we are engaging everyone who is here. And so again, so far we've just talked about the general purpose of experiments or observational studies is trying to connect together an explanatory variable with a response variable. The explanatory variable can explain the change in something else, and the response variable is the result of something else. So for example, if I have a high school track coach like me trying to identify good athletes for the long jump, and this track coach measures records the 100-meter dash times of several athletes as well as their long jump distances. If in the future that coach wants to use sprint times to predict jump distances, which of those variables is explanatory? Which of those variables is the response in this situation? And I'm going to wait about 30 seconds for you to come up with a potential answer. If you're here live, be sure to put something in the chat so I can see if you got an answer. If you're watching on replay, I'll come back in about 20 seconds with the correct answer. All right, hopefully you've gotten a chance to think about it. In this situation, the keyword is predict. The thing we're predicting is going to be the response variable. So therefore, sprint time, how fast they can run, is the explanatory variable. And the response variable, that is a result of how fast you can run, is potentially how long you can jump. One more example here. If a chef cooks several pieces of chicken and has customers rate the taste of each piece on a scale of 1 to 10, while cooking the chicken, the chef used different combinations of oven temperature and amount of seasoning. In this situation, try to identify what the explanatory variable or variables is and what the response variable or variables are. Give it about 15 more seconds. All right, so in this situation, I actually have multiple explanatory variables. At the end of the situation, the customers are rating the taste. So at the end of that, that's the response variable. But at the beginning, the chef is controlling the temperature of the oven and how much seasoning is going on the chicken. And then the taste rating is, in fact, that explanatory variable. So that's been a little bit of practice on explanatory versus response variables. Now we're going to go into the differences between experiments and observational studies. So we've talked broadly, what are statistical studies doing, trying to establish association between multiple things, explanatory versus response. And now let's get into the actual distinction between experiments and observational studies. This is a pretty key distinction that comes up quite a bit in AP scenarios, but it's also a pretty straightforward distinction to make. So observational studies are observational. You are observing what's going on. So you will record data, whether that's from the past or the present, without doing anything to the individuals in your experiment. So we're not going to assign anything. We're not going to hand out any treatments. We're just going to see who does what and start recording data based on that. So there may still be groups involved. There may be like, you know, this group chooses exercise A, this other group chooses exercise B, and then we compare maybe their weight loss at the end of the, end of a trial period and see, which group did better. But we're letting people choose stuff. We're not interfering at all. Whereas in an experiment, we are actually controlling stuff. So if you think about science experiments, you often have, okay, well, we're going to put 5 milliliters of this thing in this one, and 10 milliliters in that one, and 15 milliliters in that one, and you control what you're giving out. You're deliberately imposing different treatments and then recording data. That's an experiment. So the key distinction between an observational study and an experiment is whether or not treatments are assigned, whether or not we as researchers are actually actively manipulating the individuals in the situation, or if we're just observing what's going on without any interference at all. Okay, and that is a key distinction, and that is like the key distinction that comes up quite a bit when it comes to AP questions. So for example, let's look at some situations and decide if these are experiments or observational studies. And what do you know, people watching on replay? It's the same scenario again. So I'll give you about 15 seconds to read this first scenario one more time and then decide, is this observational or was this an experiment? All right. And I hope that you were thinking, well, I don't think the coach really assigned anything here. She didn't. She just observed what was going on. She recorded a bunch of data without giving anyone any real assignment there. This is an observational study. What about the chef situation? I'll let you read that again for a moment and decide if this is an observational study or an experiment. About 5 more seconds. And in this situation, the chef is controlling the different temperatures and amounts of seasoning that is imposing those treatments on the pieces of chicken that are being a part of this experiment. So that is, in fact, an experiment. I think you've heard me say the word treatment a couple of times. Let's just take a second to define that. So the treatment is the specific condition we're imposing on individuals. So if there are multiple explanatory variables, they might be a combination of those different explanatory variables, like in the chef situation, the specific temperature and the specific amount of seasoning combined would make a treatment. So maybe if there's 2 different temperatures and 3 different levels of seasoning, then there would be 2 times 3 would make 6 different treatments. So maybe 300 degrees and no seasoning, 400 degrees and no seasoning, 300 degrees and a little bit of seasoning, 400 degrees and a little bit, 300 and a lot, 400 and a lot, and now boom, I've got 6 different treatments that I can impose. If I just have one explanatory variable that I'm trying to measure, like let's say different types of exercise, exercise plan A versus exercise plan B, plan A, plan B can be the treatment, where the explanatory variable is which type of exercise did you get, and then we'll measure a common response variable like weight loss after 3 weeks or improvement in flexibility after a month, or whatever we're trying to figure out if there's an association between the types of exercise and some specific response variable. And so if you're justifying if something is an experiment or an observational study, the way to get that full credit where you can get a full E versus a P or an I is make sure you're explicitly naming what the treatments are. So don't just say, this is an experiment because treatments were assigned. Say, this is an experiment because the type of exercise was assigned, and specifically name what the treatment would be. So here's a long example that we're going to see for the next several minutes, and I'll do several different parts of it. So I'll give a second, I'll read it out loud, I'll give you a chance to process it, and then we'll start looking at some different types of questions that I've seen asked about scenarios like this in the past. So here's the scenario. A university hospital researcher was interested in determining the effects that pulling an all-nighter, in this case defined as getting 1 hour or less of sleep, had on a student's risk of catching a common cold. A survey was given to a random sample of 200 students at the university. The results of the survey indicated that those students who had pulled at least 1 all-nighter in the last month were 2.5 times more likely to have gotten a cold during that time. So there's clear that there's some association between all-nighters and getting colds. And sometimes we're just asked explicitly to identify the explanatory and response variables in this situation. And so I'll give you some time to think about it before I reveal answers. And I'll talk about the different scoring criteria that get used here. So take about 15 seconds to think about it. Maybe reread the situation, figure out which is explanatory, which is response. All right, hope you've gotten a chance to think about it. Here are the types of answers that the AP exam would like to see. The explanatory variable would be whether or not a student pulled at least 1 all-nighter. And the response would be whether or not a student got a cold in the last month. Yes, that whether or not is important to make it clear that there's either you did do it or you didn't. So they mentioned at least 1 all-nighter. So they're really asking people on the survey, have you done this in the last month? Potentially, maybe even how many times have you done it? So it's possible that if you say number of all-nighters pulled in the last month, that could potentially get credit for the explanatory variable. But the key distinction here is, did you do one or did you not do one in the last month? And those will be our 2 groups that we're going to compare. And then the response variable that we're comparing is whether or not you got the cold. So that 2.5 times more likely isn't the variable being measured. The variable being measured is, did you get a cold or did you not get a cold? And they're probably comparing the percentage of students in each of those groups that did or didn't get a cold. Right? Looks like we might have had another person or two join in here. If you did, be sure to say hello. We're kind of in the middle of a few things, but I think you'll be able to catch on as we go. So we've been discussing the distinctions between explanatory variables and response variables. Explanatory variable is what you control if you're doing an experiment, or the different, what can be used to predict the response variable. And the response variable is the result of the study. So in the case that we're seeing here with the university hospital researcher, the explanatory variable is whether or not you've pulled an all-nighter in the last month, which can help potentially predict whether or not you're going to get a cold. That was the result of a survey in the situation. And same scenario, we're often asked, is this an experiment or an observational study? So using our definition from earlier, where the experiment is when researchers are imposing treatments on individuals, where observational studies are if we do not impose treatments, let's take a little bit of time and see if we can figure out, is this an experiment or observational study? I'll come back in about 10 seconds with an answer if you're watching on replay. All right, this situation, the researchers were looking for an association, but all they did was give a survey. They did not tell anyone whether or not they should be pulling an all-nighter. So I would say this is an observational study. The reason being, the researcher did not assign students to pull an all-nighter or not. Notice I'm not just saying the researchers did not assign treatments. We're explicitly naming what the two different groups of students are based on the explanatory variable. People who did pull an all-nighter, people who did not. Researchers didn't tell them what to do, so this was an observational study. Okay? You will earn a P if you just say something vague like, we did not assign treatments. Okay, it's important to get that full E, the essentially correct credit that you want to get. You want to say that we didn't assign whether or not to pull an all-nighter. That makes it clear that's the treatment being assigned. We'll see this scenario again in just a couple of minutes here, but I want to talk about this thing called confounding. Confounding. If you're not sure what that means, it's kind of like a synonym for the word confusing. Not quite exactly, but similar to it. Because in an observational study, like the one that was done with the survey in the last example, people end up deciding which treatment group they end up in. So like the people in the observational study just shown, they were deciding for themselves whether or not they were going to pull an all-nighter. And if you think about the kind of people that would choose to pull an all-nighter versus the kind of people who wouldn't, there might be some common characteristics shared by those people that might also have an influence on the response being measured. So in the case of the experiment or the observational study before, the response being measured was whether or not you got a cold. There might be something about the kind of people that would pull an all-nighter that might influence whether or not they get a cold. And so a confounding variable is another variable that is not part of the study that will potentially have an impact on the response variable and also have an impact on the groups that people end up with in an observational study. And so to put one in context here, okay, let's refresh ourselves on this situation. The explanatory variable was whether or not you pulled an all-nighter. The response variable is whether or not you got a cold. We got to think about potential confounding variables that could influence whether or not you decide to pull an all-nighter and also have an impact on whether or not you get a cold. So if you think to yourself, well, what would impact whether or not I get a cold? You could think about your immune system. You could think about, your diet. You could think about, how much time you spend outside versus inside. Those could potentially all impact whether or not you get a cold, but you'd have to make a connection to, will that also impact my decision to pull an all-nighter or not? So if I'm the kind of person who does this thing, will that also influence whether or not I pull an all-nighter? And a lot of times if you're asked to write about confounding variables, the AP exam will give you a confounding variable to talk about. So in this case, they might give us level of stress, maybe a confounding variable in the study. And so you have to think about, okay, how could my stress level impact whether or not I get a cold and also have an influence on whether or not I pull an all-nighter? And so a sample response here connects it to both sides. And I'll show you a sample response in about 20 seconds. I'm going to give you a little bit of time to maybe think in your head, how could I connect level of stress to the response variable and to the explanatory variable here? And this is where you get to use your own brain and your own connections from like real life. This is not really a math problem. This is more of a logic, sciencey kind of thing. And I'll reveal an answer in about 10 seconds. Okay, so here's a scenario that the AP exam would accept as a full E, this description. Students with a high level of stress may be more likely to pull an all-nighter while also being more susceptible to a cold due to their immune system being weakened by the stress. Therefore, the association in the study may be due to either the all-nighters or the stress levels of the students. So you can see suddenly stress level and whether or not you pull an all-nighter are actually related to each other when it comes to whether or not you get a cold. And so you can't decide, if I know someone got a cold, is it because they were pulling all-nighters or is it because they're super stressed out? Because if they're super stressed out, they're also maybe more likely to pull all-nighters. And suddenly things get a little confusing, and that's why they're called confounding variables. So if you read this description, notice that I've connected having a high level of stress to whether or not you pull an all-nighter and having a high level of stress to being susceptible to a cold. You could go at it from the other side. You could potentially say students with low levels of stress may not get a cold because their bodies are strong and they're feeling good, and they're not stressed out and likely to pull all-nighters. Therefore, same conclusion. The association being seen may be due to the stress level and not whether or not they pull an all-nighter. So to recap what we've done in the stream so far, again, watching on replay, be sure to use timestamps if you want to go back and see any of this other stuff. Observational studies, we do not impose treatments on our individuals. Could result in potential confounding variables if we're not careful. Experiments, we as researchers assign the treatments to our different individuals in the experiment, and the treatment is the specific condition we impose. So it could be a combination of things, or it could just be you get exercise type A, you get exercise type B, you no exercise. And those are the treatments that we're assigning. Confounding is when, in an observational study, there's a variable that impacts both the explanatory and the response that was not controlled for because this wasn't an experiment. And so suddenly, I'm not really sure what the results are. And so confounding helps explain why observational studies, we can find association between things, but we can't necessarily say that, for example, pulling an all-nighter causes you to get a cold, because there could be a whole bunch of other things at play, those confounding variables. And when you're doing a free response question about observational studies or experiments, make sure you're referring to the specific treatments. Make sure you're using the language of the situation to help show the context and get full credit for your answers. Okay, so let's pause for a moment. We've hit what are explanatory and response variables when we're doing studies in general. We've hit the key differences between experiments and observational studies, including talking about those confounding variables. For the rest of the stream, we're going to forget about observational studies, and we're just going to look at experiments. So if you've just recently joined me live, please make a point of jumping in, ask questions. I want to make this interactive for you as well as people who are watching on replay to get what they need. And so we're going to just focus on experiments now, starting with a whole bunch of vocabulary, some of which you may have heard before, some of which you may not have heard before. And we'll talk about how AP Stats uses a lot of these phrases. So the diagram you see at the top of your page is a very basic experiment design that could be a valid experiment design for an AP Statistics course. So you'll notice that first word on the left says experimental units, which is a really fancy term. But what it specifically is it's the smallest group of individuals to whom treatments are applied. So sometimes individual people are experimental units. So if you're testing out a new exercise program versus an old exercise program, and you're going to assign people to one of the two programs, the people are experimental units. Okay, so they can be single individuals, but a good way to distinguish is, let's say you're testing out 2 brands of fish food on a bunch of fish to try to figure out which one makes the fish grow bigger. If you say that fish are the experimental units, so individual fish, you're implying that you're going to give different food to each individual fish in your experiment. A lot of times, if you're doing experiments on fish, you're going to put the fish into tanks, and you're going to put the different types of food in different tanks. In that case, the fish aren't the experimental units. The fish tanks are the experimental units because you're putting different food in the whole tank, not individually feeding each fish. Okay, so containers, tanks, whole groups of individuals, if you're assigning things to groups at a time, the groups are probably the experimental units. If you're assigning things individually to single individuals, the experimental units may in fact be individuals. You may have heard of control groups. A lot of people experience with this in their science class. Remember that that is a group that receives no active treatment. Okay, a control group might receive something called a placebo. So placebo is spelled placebo, it's pronounced placebo. Placebo is a fake treatment. So think about, I'll use a prop for this. Okay, these are Tic Tacs, just so we're clear. I'm not showing anything illegal here. But if I have a medicine that I'm trying to test out that has an active ingredient in it, I might also assign someone just a regular Tic Tac or a sugar pill and tell them, hey, this is going to impact you, but you can't tell the difference. So one of these is real, one of these is kind of fake. This thing is called a placebo. So if you're in a control group, you might receive nothing. You might receive something that looks like a treatment, but actually doesn't contain any of the active ingredient that we're doing the experiment on as a placebo. And now I'll freshen my breath. I may not do that because then I won't be able to talk. Okay, so experimental units, control groups, placebos. On this slide, we'll talk about all the features of well-designed experiments that the AP exam wants you to know. So in an experiment, a well-designed statistical experiment, you have to have comparison, meaning you have to have at least 2 treatment groups. Okay, one of those groups may be a control group or may not be a control group. Okay, but what you can't do is just say, all right, I'm going to take 25 people who experience headaches. I'm going to give all 25 of them the same medicine, and then I'm going to measure what percentage of them feel better. That would not be a well-designed experiment because you don't have anything to compare the people who did get the medicine versus another group. So you might have, let me take people who are experiencing headaches, give some of them medicine, give some of them a placebo, and measure the percentage of people in both groups who feel better. Because then you can figure out, is the treatment actually working? Or maybe you test a new medicine versus an old medicine, but you got to have some kind of comparison. You also have to have random assignment of your treatments. Can't let people choose for themselves because then you open yourself up to the possibility of confounding because it's an observational study. Random assignment can help potentially balance out some of those confounding factors that'll come up. And so if you let people choose which treatment they get, certain types of people might choose certain treatments that aren't really similar. Who gets what treatment, you should potentially balance out those differences and end up with less biased or less confounded results. You also need to have replication. This is a vocab word that a lot of students get a little bit confused. Replication does not mean repeating experiments. Say that again. Replication does not mean repeating experiments in this context. In your AP Stats context, replication means multiple experimental units receiving each treatment. So if I'm going to test out a new medicine and a placebo, I better be giving this new medicine to a whole bunch of individuals, like 25, 50, 100, something like that, and giving the placebo also to a whole bunch of individuals. I do not need to be repeating the whole experiment. I need to be repeating my treatment on multiple individuals. Okay, and as we get into the second semester and start talking about like sample size and the impact of this kind of thing, the replication will become a little bit more clear. But for now, multiple experimental units per treatment, not just repetition of the experiment. And then you might do blinding in your experiment. What blinding means is that you are blind to the treatments. So if I was giving you one of these is a placebo and one of these is real, you probably can't tell which is which because they look the same. You would be blind to which treatment you're receiving. That could be an example of what's called a single blind experiment if I happen to know which is which. But if I, as the person who's going to evaluate whether or not you're getting better, if I don't know which one contains which treatment, now neither of us know. This is called double blind. So you might have heard in a lot of like newspaper articles or potentially in the news, like according to a new double blind clinical trial, that's when, it's usually medical context. That's when the doctor's involved don't know which treatment their patient's getting. The patient's involved don't know which treatment they're getting. And so we can reduce the amount of bias, because if you think about it, if I'm going to look at a patient who I know is receiving a placebo, I might treat them differently than if I knew they were getting the real treatment. And so blinding can help potentially reduce like human biases and human errors, and just like strengthen the experiment. Sometimes it's not possible to do blinding. Okay, if I'm going to test out a new medicine that's a pill versus an old medicine, which is, you know, a spray or a liquid, you know which one is which because they're different things. And so you can't always do blinding, but if you can, it can be useful. So the list of terms on the right side of this screen, I believe we've talked about all of them so far. Experimental units, treatments, response variable, control group, placebo, comparison, random assignment, replication, blinding. The AP exam will give you a lot of different scenarios and could potentially ask you about any of these features. So multiple choice questions love doing a lot of like, which of these statements must be true based on a description? And then we'll give you a bunch of statements about these vocab terms from the situation. Even in free response questions, I've seen a lot of just identify X, Y, Z. So a lot of times they'll ask for the first three things, the experimental units, the treatments, and the response variable. They might ask you if there's a control group present. They might ask you, is there blinding involved? They might ask you, describe how to do random assignment. Okay, let's look at an example, and I'll read it out loud and give a minute and just let you try to think about all these things if you're watching on replay. And then I'll go through the list of words, connect it to the different parts of the situation, and then we'll move on to our last chunk of the evening. So a chemical company has developed a new fertilizer and designs an experiment to test its effectiveness. On 30 equally sized plots of land, 20 tomato plants are planted. The plots are then randomly split into 3 groups. One group receives 2 pounds of fertilizer per day, one group receives 1 pound of fertilizer per day, and the third group receives no fertilizer. The plots are given the same amount of water and sunlight throughout the study, and at the end of 2 months, the average weight of the tomatoes in each plot is measured. It's a lot of stuff. I will come back in about 45 seconds and start talking through some of these vocab terms. So try to identify all the different vocab terms on the side within this situation. Help see if you got it. And we are back. Okay, experimental units. That's the smallest group of individuals that receive treatments. You might be tempted to say tomato plants, but the tomato plants themselves are not individually being given fertilizer. The plots of land upon which the tomato plants are planted are receiving the different fertilizers. So the experimental units here are the plots of land, the 30 plots of land, or you could say the groups of 20 tomato plants. So there's the different groups, but it's not the individual plants themselves. It's the groups of plants. The treatments, as I've alluded to, are the different fertilizers. 2 pounds, 1 pound, no fertilizer. So it's not fertilizers themselves, it's the amount of fertilizer, I should say. So you could get credit for saying different amounts of fertilizers, the 3 different amounts of fertilizers, or listing them 2 pounds a day, 1 pound a day, no fertilizer. If you do list them out, make sure you list all of the different treatments. The response variable is the weight of the tomatoes at the end of 2 months, or the average weight of all 20 in the plots. You can probably get away with saying weights or average weights being the response variable. In this situation, there is a control group. There's a group that receives no fertilizer at all. So that control group doesn't receive a placebo, though, because they're not actually getting any treatment at all. It's not like they got new soil with no fertilizer in it and that was like a fake treatment. It was just no new fertilizer. Comparison is happening because there are 3 different groups, 10 different plots of land in each of the 3 groups. So I can compare whether or not the fertilizer works versus no fertilizer, and I can compare whether 1 pound is better than 2 pounds or vice versa. The problem explicitly says randomly split into 3 groups. So there's your random assignment. Replication happens because if you think about it, 30 equally sized plots can be split into 3 or three groups of 10. So there's 10 plots getting each of the 3 treatments. And so we do have replication. And blinding here, I mean, plots of land aren't people, so there's not really blinding there. But if I, as the person who's measuring the weight of the tomatoes at the end of the study, if I don't know which plot the tomatoes came from and all I was doing was weighing them, then I might be blind to the treatments. So there could be a single blind experiment here, but I don't really know that it would be double blind. I guess maybe if the person, because you know if you're putting fertilizer in, so I don't think it could be double blind. So lots of vocab terms here on the side. Go through them. Be sure to ask if you have any that you're struggling with that we can potentially go over again. But for the last little bit that we're doing here, we've talked about what is an experiment versus an observational study, the features of good experiments, and now let's hit some types of experiments that you get asked about quite a bit. Okay, so the first type, the design you saw earlier, is called a completely randomized design. And this is when experimental units are randomly assigned to treatment groups without doing anything else first. No previous grouping. The example you just saw with the tomato plants was a completely randomized treatment, or completely randomized experiment. 30 plots of land, split them up into 3 groups of 10, and then start giving out fertilizer. Okay. You may be asked to describe how this happens. So you may have to say, describe a process to assign the 30 plots of land to their different treatment groups. And in that case, you might want to use a random number generator description where you say something like, assign each plot of land a number between 1 and 30. And then you would start generating a list of numbers between 1 and 30. And this should sound similar to what you do with a simple random sample. So I'm going to send just like a quick shout out to, if you go to another stream that we've done, we talk about how to describe simple random samples. That's a similar strategy you can use to describing completely randomized design. And in future streams, as we practice more general free response questions with experiments and surveys, we'll be sure to bring up a couple examples of that. For the time being, we're just talking about the different types of design. So that's not really one of the main focuses of this stream. And this style is like a pretty classic style. And it's good if you have similar experimental units to each other. So if you've got 30 plots of land in the same general area, same amount of sunlight, same types of soil, probably going to be good to go. But if your experimental units have some differences between them and you think they might impact the results of the study, like some of my plots of land are, in a desert and some of my plots of land are in a rainforest, tomatoes might grow differently in those two admittedly extreme environments, probably not going to be that extreme. But if you have different types of individuals in your study, you might want to use what's called a block design. Okay, you can see at the bottom, blocking is designed to help reduce the variability in response and allow easier comparison of treatments. What do I mean by that? Okay, what I mean is we're going to randomly assign treatments after we do some kind of non-random grouping. Because if there are people with common characteristics or things with common characteristics that you think will impact the response, it probably makes sense to split them up. To give a contextual example here, one that I like doing in my class a lot is if you think about trying to test out, all right, we're going to race a bunch of dogs. And my mom has adopted greyhounds. They love to run. They love to race. When they're retired, sometimes they need a good home, so we've given them a good home. But if you think about greyhounds running super fast, super lean, they're built for it. If I was going to have a greyhound run an agility course or run a track race against a pug, for example, wouldn't necessarily be a fair race. And so if I'm going to test out maybe 2 different types of dog food and see which one helps the dog get faster, it wouldn't be fair to have different types of dogs racing against each other. So why don't we start by getting a whole bunch of dogs, splitting them up into their different breeds or even just different sizes, then assign the dogs to get either food A or food B, then race them against each other. There was an AP example several years ago involving like professional runners versus recreational runners. And it would make sense to separate the professionals versus the recreational runners because they're going to be wildly different speeds. And so that's helping to reduce variability. If you have only professionals receiving different treatments and racing each other and comparing the response, and only recreational getting different treatments, racing each other, having a response, you'll have reduced the amount of variation in those groups, and it'll make comparing the treatments a little easier. Okay, if you think about the dog example, if I have just greyhounds, 2 types of food, assign them, and then race them, it'll be easy to tell if there's a difference in the food because their times should be relatively similar because they're the same breed of dog. And so if you're thinking about blocking, you need to ask yourself, is there a common variable that will impact the response in this experiment? And could I separate individuals based on that variable before assigning treatments? If you notice, within the blocks, you're basically doing a completely randomized experiment and comparing results at the end. So you're going to assign randomly what treatments there are after non-randomly separating folks. Okay, some common blocking variables, potentially genders, age levels, previous experience with things. All those could be good examples. One more type of experiment is going to be a special type of blocking called matched pairs. And so if you look at this diagram, it looks kind of complicated, but if you notice, the only difference between that and block design is instead of saying blocks, it says pairs. So there's one type of matched pairs design where you randomly assign treatments after grouping individuals into twins, like find a matched pair. So in the runner example, you might find 2 runners who are similar size, similar build, similar strength, similar speed, assign them 2 different treatments, have them race each other, see which one worked better. In that case, though, you'd have to make sure you have multiple pairs to ensure replication. You want to get multiple individuals with each treatment, which is why you see pair 1, pair 2, et cetera, et cetera. There is a second type of matched pairs design, which is when you use yourself as a matched pair, where every experimental unit gets both treatments, and the order in which you receive the treatments is then randomized. So, for example, if you're trying to test out something that involves like throwing things, you might have people test throwing with their dominant hand and their non-dominant hand and compare between them. Then you would randomize which hand goes first, or which ball you put in which hand. If we're testing out 2 different balls, which one goes farther, something like that. I've seen examples on AP exams before about like different brands of like suntan lotion. So if I'm going to do a matched pairs experiment with that, I could find people with similar skin tones, like similar ability to get sunburned, and assign them in pairs. Or you could just use yourself. Put one brand on one arm, put another brand on the other arm, and now you're a matched pairs experiment because you're comparing both treatments on yourself. So we've got completely randomized experiments where there's no grouping before we assign treatments. Randomized block design where we make groups based on a shared characteristic, then assign the treatments. Or matched pairs where we make either twins or everyone gets their own specific treatment. Okay? And at this point, this is it. We've seen the different types of statistical studies on a broad overview, explanatory versus response. We're always trying to connect association. Does this thing impact this other thing? We can do that via experiments or observational studies. Observational studies, we don't impose treatments. Experiments, we do. If we're doing an observational study, we open ourselves up to possible confounding. If we do a well-designed experiment, there's a whole bunch of things we need to have. Comparison, replication, we could potentially use blinding, we might use a control group, we might have a placebo, and there's a lot of vocab terms that we need to make sure we're familiar with. And then the different types of experiments, completely randomized, randomized block, matched pairs. They have their pros and cons, but it's important that you know which type is which. And at this point, if I don't have anyone who's live and has any questions, if you're watching on replay, feel free to go back using the timestamps to check out any of those previous notes, I guess, or previous examples. And at some point soon, be on the lookout. We'll do a review stream about collecting data. So we'll talk about surveys, sampling methods, sources of bias, types of experiments, observational studies. We'll do a bunch of multiple choice and free response style questions based off of previous exam questions that will review these concepts. And so with that, doesn't look like I have any questions for me. Thank you so much for watching, and I will see you next time. Once again, this has been Jerry Krossoff with Fiveable. Be sure to follow us and get all your updates for future AP stats and other AP content. Thanks for watching.